So the lecture is started. So what we have seen in our last class is that we talked about I asked you to write over here that quarks experience both strong and weak force, whereas leptons experience only the weak force. Now, about this strong and weak force, let me just elaborate these things a little bit. In nature, by the observation of the scientists, there are four primary type of forces. Number one is gravitational force. Every object that is defined as an object, not energy, and everything that has mass, measurable mass, is subjected to gravitational force. No matter how small, no matter how big, no matter how tiny, or doesn't matter. Uh, Everything that has mass is subject to gravitational force. The second force is electromagnetic force. Electromagnetic force is a force that is experienced by everything that has charge. Stationary charge particles are subject to electric force. Moving charge particles are subject to electric and magnetic force both. Because, well, pretty much, if you think for the entire universe, motion is practically a relative thing. One object is in motion with respect to another. So everything is in movement. So depending upon relative motion, objects can be subjected to electromagnetic force, but only charged objects experience the electromagnetic force. Neutral objects do not experience electromagnetic force. These are the two types of force which are typically observed in our regular life experiences. I mean, all the type of force things that we see, for example, pushing, pulling, friction, rubbing on, or any other type of forces, they are basically these two type of forces. If you think that, if you let's say you are currently sitting on the chair or on your bed or any surface, you have to think that all the particles of very lowest particle of your body, very lowest atoms of your body, have outer shell layer electrons, and those electrons are repelling the electrons of the surface that you are sitting. So those electrons are practically repelling each other. The closer those electrons get to each other, the stronger is the repulsion. So mathematically, it is possible that using your entire weight and compare and considering all the electrons which are undergoing these repulsive forces, we can calculate that what is the actual gap between those two atoms electrons, which essentially means that all of us, no matter our position or our structure or age, whatever, all of us are practically levitating on a certain surface, because there is always some bit of gap. Without covalent bonds or metallic bonds or ionic bonds, particles are always practically not in contact with each other, because the outer shell electrons will always repel each other. This is a very interesting information, but it can be hard to visualize because this is something that we are not acquainted to. We see objects touching each other, but practically speaking, or at minute level, there is no true touching. Nothing touches anything because of the repulsion between the electrons.
Sir, then how do we feel the chairs when we sit on them?
সরি, যারা বুঝি নাই আরেকবার বলো।
স্যার, যদি কোনো টাচিংই না থাকে তাহলে আমরা যে সারফেসের মধ্যে বসি সেটা আমরা কেমনে ফিল করি?
Because we sense that repulsive force, but that doesn't essentially come through contact. Think about it. I mean, if you think about, I mean, one way to visualize this thing for a macro scale or for our regular life experience is that if you keep two magnets of similar poles facing each other, and if you start to bring them closer, you will see that before touching they are pushed away from each other, right?
Yes, sir.
Something exactly similar to that, but at a very minute level, at a very small scale.
আচ্ছা, স্যার।
Okay. So these are the two forces that we experience in our regular life. The other two forces, strong force and weak force, these are forces which are only applicable for a very small range. And that range happens to be nearly equivalent or comparable within the diameter of the nucleus. So strong nuclear force and weak nuclear force are exclusive forces which are capable of interacting within extremely close distance. So you have to, as we all know, that atoms are actually really small. I mean, the nuclei are really small. One of the physical representation for the atom is that if we could expand out a whole atom, if you think of a regular stadium, let's say an Olympic stadium or something like that, or a football field, if you place a small motorshooty PEA at the center of the kickoff point, and consider the first row of the people in the gallery as the first shell of the electrons, that is a more or less physical comparison. When if you think for the size of the size comparison for the nucleus size and the first shell, Second shells, third shells are even further away. So that is a highly magnified view to give us an idea of scale, that how small the nucleus is compared to the entire volume of the atom, which means, and strong nuclear force and weak nuclear force only work within the diameter of the nucleus, which means their effective range is extremely small. They can prove to be very strong forces. The type of their for these forces are not very elaborately discussed in your syllabus. The reason I'm telling you this, because in the definition of quark and lepton, we have these two terms. That's why I'm giving you this much elaboration. But you will never be asked about this elaboration. But anyway, if the examiners feel like that, well, the idea about these forces fall within the shaded boundary of the syllabus, and we can actually set a question about this, because if a student have learned that quarks experience strong and weak nuclear force and leptons only experience weak nuclear force, they are supposed to ask that what these forces are, so they might actually know. So let's set a question about the type of these forces, so they can do that. You cannot actually deny that their action. So if these kind of questions actually do show up, that's why I'm giving you this information. This will be also available in the recording as well, so if you ever forget these stuff, you can look them up in the playlist. That's one thing. And how these strong nuclear force and weak nuclear force actually work, and eventually how this whole thing lead to different type of radioactive processes. For example, nuclear decay, nuclear fission, or nuclear fusion. These are the three type of nuclear reactions that we experienced so far. Basic natural decay, and then we can have nuclear fission, which is a bit of an artificial decay. We hit an unstable nuclei with a neutron, and then the neutron gets absorbed within the nucleus, and then it creates the instability significantly big over a fraction of a time, and then the nucleus breaks down into smaller daughter nuclei, and some free neutrons are also produced, like crumbs of a biscuit, and then some amount of energy is released out of this process. This is called fission, and fusion is basically the merging of smaller nuclei into bigger nuclei, pretty much the way every star produces its energy by fusing the hydrogen atoms into helium. That's the primary reaction that happens all over the universe. That is the most common reaction, nuclear reaction, that is available in nature. Every glowing star has this reaction within their core. When hydrogen gets finished, and the core is depleted of hydrogen, there is no more hydrogen. If the star is strong enough, or if the star is massive enough, or the gravitational force of the star is really powerful, we can also have secondary or tertiary level fusion process. In those processes, helium nuclei start to fuse into each other and can give rise to elements like carbon, hydrogen, or those things. And those reactions, the secondary level or the tertiary level fusion processes, are extremely energetic, like super extremely energetic, like way too much energetic. These are the processes which happen for the supernova kind of thing. Anyway, that's not a part of our deal. I just traverse a bit pretty far away to give you a concept that how this thing is involved. So these are the two definitions that you have to remember, which you have written in the last class, and I'm going to go down further to describe what is over here. One of the things that I would like to tell you is that for this upcoming part of the lecture, there are a lot of stuff that you have to remember / memorize. Remember is actually just a better word, better sounding word, not a better word, essentially not a better sounding word than memorize, but you have to actually memorize a couple of information. For most of the parts, the why part would not be answered. Whether why does it happen like that, that is not covered in your syllabus, so I'm not going to go there. I'm going to mostly tell you what is happening and what happens. So the information is provided, but the feedback or the reason why that thing happens in that manner, that will not be provided for your syllabus content. So we'll just say mostly the what part of the whole information. I'm telling you this part as a disclaimer, because you might have those questions, and you are welcome to have those questions. Can only have questions whenever you're thinking about something, and thinking is basically how you learn. So I appreciate that, but I am telling you this firsthand, so that whenever I tell you that I cannot tell you this answer, you do not essentially get disheartened. So that's why I am telling you this. So these are the charts that we have. Have a look over here. There are 6 quarks defined so far. Like quarks, there is another group of subatomic particles. They are called leptons. Each of these 12 particles has their own antiparticle. So there are 6 quarks and there are 6 leptons. These are the primary 12 fundamental particles that we have, the scientists have defined. So interesting information, or let's say a correction of your earlier known information. Up till now, you have known that the fundamental particles are electron, proton, and neutron. This was the actual true guess of scientists for a really long time. And then over the duration of the progression of science and technology, scientists eventually made the LHC, the Large Hadron Collider, which is in Switzerland. Goes over multiple countries. It is actually a mechanism by which you can shoot really high speed charged particles within each other. and actually break them apart into their much smaller pieces. This is the purpose of that machine. Now, whenever the scientists started using those machines, they actually found out that electron happens to remain electron. Electron doesn't break off into anything smaller. Electron remains electron no matter what. However, protons and neutrons are actually broken down into multiple other things. Protons and neutrons are actually divisible into much smaller entities. Those smaller entities are actually the quarks and the leptons. So this is the basic idea that, so we have six quarks. They are named like this: up, down, charm, strange, top, bottom. Don't ask me why do they have name like this. Scientists chose these words, and that's the way we learn it. So there is an explanation. So these are the six quarks over here, and their symbols are basically a small letter alphabet, and they're the small letter alphabet of their first of the name. Up is U, D, C, S, T, B. All of them are small letters, and their charges are fraction. আচ্ছা, এখানে তোমরা একটা জিনিস করো, সেটা হচ্ছে চার্জ। এখানে আছে +3/2, এখানে ই লিখো, +3/2 small e, মানে write e over here. Let me show you. Let me bring this PDF over here so that I can actually show you the possible changes. Just a second. Several pages. Good. So yeah, what I'm proposing that you write +3/2 e plus 1/3 e. Write e's everywhere. I'll tell you what this e is in a moment. I'll show you a documentation to make sense. You don't have to write e beside the 0 because 0 is 0. হ্যাঁ, ভুল করছি। হ্যাঁ, চার্জগুলোতে ই হবে, ব্যারিয়ার নাম্বার লেফট নাম্বার ই হবে না। হ্যাঁ, কি করছি, I was carried away. My bad. আচ্ছা, এই ব্যারিয়ার নাম্বার বা লেফট নাম্বার জিনিসগুলো কি সেটা আমি বুঝাবো। আপাতত এই জায়গাগুলোতে ই লিখে নাও। E basically means the elementary charge. Elementary charge means the value of charge that we scientists have calculated by Millikan's experiment first, and then we actually came to know this is basically the charge of an electron, the numerical value for the charge of the electron. You can find this value in the data sheet. This will be always provided in your data sheet. So let me just show you where one of the examples. We choose any of the random year and go to, let's say, 1 QP11 maybe. And then if we have a look over here, elementary charge E equals to 1.60 into 10 to the power minus 19 coulomb. This is the value of E, or the basic magnitude of elementary charge in terms of coulomb. You might wonder that, well, if it is the elementary charge, why don't we define this as 1 coulomb? I mean, this is the smallest value of charge. Well, the thing is, scientists actually came to know about the charge value of the elementary charge value of electron far later compared to the time that the unit of charge was defined. Unit of charge was defined depending upon the experiments done by scientist Coulomb, and it was named after him. And at that point, Coulomb was defined by some physical constraints. And later it was found that the elementary charge value, or the charge value of an electron, is actually far too smaller compared to 1 coulomb. 1 coulomb is actually a massive amount of charge, like a supermassive amount of charge. So that's the value that we have, and we still use it for our practical purposes. So this is the value of the elementary charge. You don't have to memorize this value. This will be always available in your formula sheet. So this is just a good information for you. The other thing that I was trying to get at is over here, is that these values of charges are all fractions of the elementary charge, which means up quark has 2/3 the electric charge of a proton. I'm using the term proton because here we have a plus sign. Up charge has 2/3 the charge of a proton. Down quark has minus 1/3 charge of an electron. Sorry, 1/3 charge of an electron, and so on and so forth. The easier way to remember this sequence, you can see over here that the charges are changing in a pattern: +2/3, -1/3, +2/3, -1/3, +2/3, -1/3, +2/3, -1/3. This is the pattern of the magnitudes. And if you remember these name very within this sequence, I mean, you just have to take your time, or just write them somewhere and read them every once in a while, whenever you're moving around or on your table somewhere, and remember them in this sequence. If you remember them in this sequence, then this table actually will become easier for you to remember: up, down, charm, strange, and top, bottom. So if you ask me, typically students don't have confused between up down or top bottom because they are pretty much similar stuff. They usually mess up between charm and strange. I mean, they forget that whether the strange is on first or the charm is first. I have a small way to remember this thing, that if you ever forget between these two names, that charm and strange, which one is first, just remember that they have an alphabetical order. C comes first alphabetically and then comes S. So you should know that charm is on the top and S is on the bottom. So that can help you, because that's how I remember if I ever feel confused that which one is above. So up, down, charm, strange, top, bottom. And this is the sequence of the value of their charges. And I'm going to talk about barrier number after a while because I haven't yet defined barrier. So for that I may forget about this. We'll get back to this point after a while. So these are the 6 quarks that we have. And all of these quarks, each of these quarks can have their own anti-quark, which means basically that in this table we have 12 fundamental particles. 12 fundamental particles. Each particle can have their own antiparticle. Now antiparticle is actually a pretty interesting concept. Antiparticular definition এখানে কোথায় যেন দেওয়া আছে, we can should be able to find it. আচ্ছা, এখানে লেখা আছে, each of these 12 particles has their own antiparticle. The antiparticle has every property opposite to a particle except mass, which means the particle and its own antiparticle are equal in their mass property, which means there is no negative version or there is no reverse version of mass. If an object has mass, it has a positive value of mass. If an object doesn't have mass, it's not an object anymore. So mass doesn't have an opposite property. For example, let's say you can have positive charge and negative charge, but you cannot have positive mass and negative mass. That's not how things work. So particle and an antiparticle being two entities, they will have the same amount of mass if they are for the same variation. Let's say an up quark has the same mass as an anti-up quark. Anti-up quark, that's the name, anti-up quark. But all of the other properties would be exactly opposite, which means the charge of an anti-up quark would be minus 2 by 3e. Up quark has a charge of plus 2 by 3e, so the charge of an anti-up quark would be minus 2 by 3e. The baryon number for up quark is plus 1 by 3. I'll explain where does 1/3 come from. But and also the baryon number for the anti-up quark would be minus 1 by 3. So every numerical value for one particle and its antiparticle are exactly opposite to each other in terms of plus and minus, except for mass. So these quarks can have 6 of their antiquarks, and these leptons can have 6 of their antileptons. So if you have a look at this list, you have to understand that electron is the first particle. Electron is given by E minus. This is a very early sign that we adopted, and this one's charge is minus 1e, and it has a lepton number of plus 1. Because this is a lepton, that's why it has a full lepton number of plus 1. The second particle is electron neutrino. Electron neutrino is not the antiparticle of electron. This is the key part you have to understand. Electron is a particle. Electron neutrino is also a particle. It is named in such way because typically, whenever through any atomic process, any atomic breakdown process, electron comes out of that reaction. Typically, we also get a subsequent emission of an electron neutrino, or we might also see an anti-electron neutrino. So, because these two things are pretty very much what can I say, closely related in terms of the outcome of a nuclear reaction, that's why it is named like this. So you can see over here, basically there are 3 neutrinos: electron neutrino, muon neutrino, and tau neutrino. So all of these three are neutrinos. Neutrinos have zero charge. They don't have any charge at all whatsoever. So neutrinos have zero charge. But in terms of name, it is electron neutrino, electron neutrino, 2 particles, muon neutrino, 2 particles, then tau and tau neutrino, 2 particles. Once again, if you forget this sequence, if you have to remember the names, there is no alternative to that. So electron, mu, and tau. If you forget this sequence, just remember that these 3 things are also alphabetic. You can see that E, then M, then T. So electron is first. Obviously, right after that comes electron neutrino. Muon is after, and then muon neutrino, and then tau, and then after is tau neutrino. So these are the particles. আচ্ছা, ব্যারিয়ার নাম্বারটা নিয়ে আমি একটু আলাপ করতেছি, বাট বিফোর আই গেট ইনটু দ্য ব্যারিয়ার নাম্বার অর দ্য লেপ্টন নাম্বার, এই পর্যন্ত বুঝে গেছে কিনা, মানে এই কলমটা পরে আলাপ করতেছি, বাট এই পর্যন্ত কোনো কোশ্চেন আছে কিনা বলবান, দেখো, এনিওয়ান ইফ ইউ হ্যাভ এনি কোশ্চেন।
স্যার,
ইয়েস।
এগুলো তো প্রোটনস আর নিউট্রনস থেকে আসছে, তাই না?
Yes and no. The reason I'm saying I'm giving such a confusing answer because these are the subatomic particles, which we have defined as fundamental particles. Because we just came to know about the idea of antiparticles, you have to understand that a proton can also have an antiproton. Proton is written by small p. Antiproton is written by a small p bar. Antiparticles are written with a bar sign on their top. For example, an up quark is U, and anti-up quark would be U bar. Down quark is D, and anti-down quark would be D bar. So we give a bar sign on the top. So the question that you asked me that all of this should come from protons and neutrons. Well, not essentially. They could also come from antiproton and antineutron. And apart from proton and neutron, there are many other composite particles. These things somehow merge up to produce protons and neutrons. But protons and neutrons are the only two particles that you have come to know across so far up till now. That atoms are made up of three types of particles: proton, neutron, and electron. Proton, neutron stay in the nucleus, and electron goes around circular orbits. Not circular. Electron goes around in orbits around the nucleus. That's what you've learned so far. But now you're learning a much deeper information that protons and neutrons are also breakable. So so antiprotons and antineutrons are also breakable. So these particles doesn't essentially come out of proton and neutron. They can also come from antiproton and antineutron. And apart from proton and neutron, there can be other composite particles as well. I mean, you can merge, let's say, one up quark with one anti-down quark. You can get a meson. Now, meson is another genre or another species of composite particles. Composite particle, both I'm using the term composite particle to give you an idea that whenever two or more of these things, of these 12 fundamental particles, or they are associated antiparticles, so altogether there are 24. Whenever more than one or two or more of these particles and antiparticles merge together to produce a stable particle, we can call it a composite particle. Which we will say.
Yes, sir.
So they don't essentially come out exclusively out of proton and neutron. They can come out from other composite particles as well. Acha, any other question? Anyone?
এই জন্যই তো স্যার এগুলোর নেগেটিভ চার্জও হইতে পারে।
Yeah, they can have auto. We're gonna see about this equation after a while. এই equation একটু পরে বলতেছি, but এই টেবিলে নিয়ে আর কোনো কোশ্চেন থাকার actually জায়গা নাই, কারণ because these are all just telling you what value is there. The next part that we're gonna see is right over here. We have proton. Proton is labeled as 1p1. This is the basic symbol for proton. We have known this for a very long time. A proton can be also written as the hydrogen nucleus, so we can also write this as A1H1. This is also the symbol for proton. Both of them can work. Scientists found out that proton is made up with three quarks up, down. This is a finding. Why they are made up of up, down? I don't have this answer. I don't have this answer. Scientists found out that they are made up from up, down. So these three quarks merge together to produce one proton. One of the ways that we can see over here that the total charge of the proton is given by plus 2 by 3 and plus 2 by 3 plus minus 1 by 3. So up quark charge is plus 2 by 3, up quark charge is plus 2 by 3, and down quark charge is minus 1 by 3. You can essentially write a total E over here, or you can write individual E's over here. That would be a better thing. And then this got 3 by 3 E. Here is a plus sign, and so plus 1 E. That's the whole value of this thing. So proton has plus 1 E, or plus 1 charge in terms of elementary charge value. One neutron was found out to be constructed using three quarks, and the composition of neutron is up, down, down, up, down, down. So you can see that both of them are produced from up or down, but here we have two up quark, one down quark, and in the neutron we have one up quark and two down quark. If you calculate the charge of this neutron, up quark has plus 2 by 3, down quark has minus 1 by 3, and this down quark also have minus 1 by 3. And you can also write E's over here, and I recommend that you write this in your notes right now. And altogether, if you do the sum of this thing, you get 0. For your exam, this page is really important. Sometimes, in many cases, they ask you to show that using the quark model, explain why the charge of a proton is plus 1 E, or using the quark model, explain why the neutron's charge is 0. So এই কোশ্চেন তারা করতে পারে, সেক্ষেত্রে আমাদেরকে এই কোয়ার্কের ভ্যারিয়েশন গুলার চার্জ গুলার এই প্রসেসটুকু দেখাইতে হবে। এটা বুঝা গেছে? বলবান এনি কোশ্চেন?
Yes, sir.
আচ্ছা, কোশ্চেন নাই।
ইয়েস স্যার।
এরপর জিনিসটা আমরা দেখবো সেটা হচ্ছে যে ডিকের সময় কি হয়। আচ্ছা, বিফোর আই গেট ইনটু দ্য ডিকে, লেট মি এক্সপ্লেইন দ্য ব্যারিয়ান থিং। ব্যারিয়ান থিং এর এখানে অ্যাকচুয়ালি জিনিসটা লেখা নাই আমাদের এখানে। অ্যান্টিপার্টিকলস, বেটা প্লাস ডিকে, ইন কপি, এগুলো লেখা আছে। আমি তোমাদের কিছু জিনিসপত্র বলবো, যে তোমাদেরকে ম্যানুয়ালি লিখে নিতে হবে। তোমরা একটা কাজ করো, আহ, এখানে স্টার মার্ক দিয়ে একটা জিনিস লিখো, এখানে লিখবা নাকি অন্য জায়গায় লিখবা, জায়গা আছে কোথায়, এখানেও জায়গা আছে। আচ্ছা, এখানে স্টার মার্ক দিয়ে একটা জিনিস লেখা শুরু করো, একটু ছোট ছোট করে লিখো, অনেক বেশি ছোট ছোট করে না, এখানে আবার ধরো 4 থেকে 5টা লাইন লিখতে হবে, 4 থেকে 5টা লাইন আটানোর মতো করে ছোট ছোট করে লিখো। এখানে এখানে একটা জিনিস লিখো, আমি বলতেছি। Whenever two or more fundamental particles, whenever two or more fundamental particles bracket out of 24 of them, out of 24 of them, out of 24 of them, dash dash 12 particles, comma 12 antiparticles, bracket close, merge together merge together, we call it a composite particle. We call it a composite particle. Full stop. We call it a composite particle. Full stop. এর নিচে একটা বুলেট দাও, একটা বুলেট দিয়ে লিখো, এটা কি এখানে আছে? এখানে মনে হয় নাই, আমি দেখলাম না, আছে না নাই? নাই। একটা বুলেট দাও, বুলেট দিয়ে লিখো, any particle having at least one quark or one antiquark any particle, or you could write any composite particle, any composite particle having one quark, 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 having one quark or one antiquark, bracket at least, অথবা at least যদি প্রথমে লিখে থাকো তাহলে এখানে লেখার দরকার নাই, আমি অ্যাকচুয়ালি মানে কথা খেয়ে হেরে ফেলতেছি। Any composite particle having at least one quark or one antiquark is generally called a hadron, HADRON, is generally called hadron, HADRON. Hadron ওয়ার্ডটা আনলাইন করে রাখো because this is a noun, জাস্ট নতুন ওয়ার্ড সেজন্য, ফুল স্টপ। সেকেন্ড বুলেটে লিখো, when three quarks, when exactly three quarks merge together, the composite particle is called a baryon. Baryon spelling টা আগের পৃষ্ঠাতে দেখে লেখো। When exactly three quarks merge together, comma, the composite particle is called baryon. Full stop. একই বুলেট লিখতে থাকো, পরের সেন্টেন্সটা একই বুলেট হবে, নতুন বুলেট না, একই সেন্টেন্সে লিখো, merging of exactly three antiquark creates an antibaryon. অ্যান্টিব্যারিয়নের অ্যান্টি এবং ব্যারিয়নের মাঝখানে একটা হাইফেন হবে। This is one word but slightly separated. Merging of exactly three antiquark, merging of exactly three antiquark creates one antibaryon. ফুল স্টপ। এর নিচে বুলেটে লিখো, না এর নিচে বলে না, ওই প্যারাগ্রাফে একটা জিনিস লেখো, protons and neutrons are the most common example of baryons. Protons and neutrons are the most common example of baryons. লাস্ট সেন্টেন্সটা কি লিখছো?
Sir, protons and neutrons are the most common examples of baryons.
আচ্ছা, এরপরে বুলেটে লিখো, এরপরে বুলেটে লিখো, one quark and one antiquark can merge together to produce composite particles which are called mesons, MESONS. এসটা হচ্ছে প্লুরালের এস, they are singularly they are called mesons, full stop. আচ্ছা, এইখানে এইটুকু পর্যন্ত লেখা হলে হয়েছে। আর তোমরা একটু ওয়ার্কশিটের আগে যাও, যেখানে যে অ্যান্টি পার্টিকুলার ডেফিনিশন ছিল না, যে এখানে দেখছো, এই যে এই জায়গাতে আমি যেখানে মাউস রাখছি, এখানে একটা সেন্টেন্স লিখো, এখানে একটা সেন্টেন্স লিখা তো বাকি পড়ছে, এগুলো আমার থিওরি করতে হবে। এখানে একটা সেন্টেন্স লিখো, হ্যালো,
জি স্যার,
Hello,
জি
sir.
স্যার, শুনতে পাচ্ছি।
আচ্ছা এখানে একটা সেন্টেন্স লিখো, whenever one particle, whenever one fundamental particle, না সরি ফান্ডামেন্টাল না, কারো whenever one particle, এটা কম্পোজিটের জন্য অ্যাপ্লিকেবল, ফান্ডামেন্টালের জন্য অ্যাপ্লিকেবল, সো ওয়ার্ডটা লেখা দরকার নেই। whenever one particle merges with its own antiparticle, whenever one particle merges with its own antiparticle, comma, together they vanish slash annihilates each other. Spells like A-N-N-I, annihilation. ANNIHILATE, annihilate হবে কারণ দুইটা পার্টিকেল বলছি। Together they vanish slash annihilate each other, and the total mass of both the particles, is converted into energy. The total mass of both the particles is converted into energy following E equals to 2mc square. আমি লিখছি এখানে, ভিডিও থেকে দেখে রাখো। Following E equals to 2mc square. 2m কেন লিখছি বুঝছো?
দুইটা পার্টিকেল।
দুইটা পার্টিকেল।
Beautiful. 2mc square. Full stop. This process is called annihilation or annihilation. That's the appropriate pronunciation. But spells like annihilation. 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 আচ্ছা, আবার একটু এই জায়গাতে যাও, মানে একটা জিনিস মাথায় আসছে, একটা জিনিস তোমাদেরকে লেখাই দিছি। আবার একটু এই জায়গাতে যাও। এখানে কি আর জায়গা আছে? এখানে যদি জায়গা না থাকে তাহলে এই মার্জিনে রাখো।
কপিতে লিখলে হবে
না, এখানে যদি না, এখানে লেখো। কপিতে লিখলে
এখানে মডেলের নিচে জায়গা আছে অনেক।
এখানে এই জায়গাতে। আচ্ছা, একটু আগে কথাগুলো তোমার
মডেলের
কোয়ার্ক মডেল। ও আচ্ছা, এখানে জায়গা আছে। আচ্ছা,
সেকেন্ড পেজে এই আপনার এই
হ্যাঁ পাইছি।
নাই
এখানে তো এখানে স্টার মার্ক যেটা জিনিস লিখতে পারো। অবশ্য আমি চাইতেছিলাম যে এটা এখানে লিখলে ভালো হতো মনে হয়। আচ্ছা, সমস্যা নাই, এখানে লেখো, এখানে লেখলে হয়েছে। ইভেন্চুয়ালি whenever you learn information will be helpful anyway. এখানে স্টার মার্ক যেটা জিনিস লেখো, সেটা হচ্ছে baryons are mesons and mesons can exist independently. Baryons and mesons can exist independently. Full stop. Leptons can also exist independently. Full stop. However, individual quark or antiquark cannot exist individually. Individual quark and antiquark cannot exist individually. Full stop. This is why quarks are given a property called baryon number. This is why quarks are given a property called baryon number. This is why quarks are given a property called baryon number. Comma, not quark number. নটটা অল ক্যাপসে লেখো, বড় হাতের এন, বড় হাতের ও, বড় হাতের টি, নট কোয়ার্ক নাম্বার। ফুল স্টপ। And comma, leptons are given a property called lepton number. Leptons are given a property called lepton number. Full stop. নিচে প্যারাগ্রাফে লিখো, so every quark has a baryon number of +1/3. So every quark has a baryon number of +1/3 and a lepton number, and every antiquark has a baryon number of -1/3. Has a baryon number of -1/3. Full stop. একটা স্কোয়ার ব্র্যাকেট দাও, স্কোয়ার ব্র্যাকেট দিয়ে লিখো, there is no such thing as anti-baryon number. There is no such thing as anti-baryon number. Anti-baryon space number. There is no such thing as anti-baryon number. লিখছো?
Yes, sir.
তার নিচে লিখো সিমিলারলি, কমা, মানে এই প্যারাগ্রাফটা তোমার নিজে দেখে লিখবা, আমি পুরো লাইনটা বলে দিচ্ছি। কোয়ার্কের প্যারাগ্রাফটার দিকে তাকাও এবং আমি লেপটনের প্যারাগ্রাফটা বলতেছি। তোমার লিখবা হচ্ছে সিমিলারলি every lepton has a lepton number of +1 and every anti-lepton has a lepton number of -1. Bracket, there is no such thing as anti-lepton number. বুঝছো? আচ্ছা, কোয়ার্কের ব্যারিয়ার নাম্বার কত লিখছো? +1/3 লিখছো না? +1
Yes,
লিখছো?
sir.
বলমান আমি ভুলে গেছি, আমি তো কারো লেখা দেখতেছি না। কোয়ার্কের ব্যারিয়ার নাম্বার +1/3 and অ্যান্টি কোয়ার্কের ব্যারিয়ার নাম্বার হচ্ছে -1/3। 1/3 আমি কি 1/3 বলছি না 1 বলছি?
1/3 বলেছেন।
ঠিক আছে, বাট লেপটনের জন্য কিন্তু 1 হবে, মানে every lepton has a lepton number of +1 and every anti-lepton has a lepton number of -1. এটা গুছায় লেখো সবাই। I'll give you 1 minute. I'm back. লিখতে পারছো?
Yes, sir.
আচ্ছা, এখন আমরা কিছু নিউক্লিয়ার রিঅ্যাকশন দেখবো এবং নিউক্লিয়ার রিঅ্যাকশন
Sir.
আমরা একদম কোয়ার্ক লেভেল পর্যন্ত দেখবো। বলো,
Sir, where can I get this note?
do you not have booklet 3?
No, sir.
What else do you not have? What do you have?
Sir, I don't have any booklet.
Did you only sign up for our mock processes?
No, sir.
How long have you been doing classes with us?
Sir, since September.
ঠিক আছে, আমাকে মেসেঞ্জারে একটা মেসেজ দিয়ে রাখো যে তোমার কাছে কোনো বুকলেট নাই। I'll look into it.
Okay, sir.
আমার পার্সোনাল মেসেঞ্জারে, টেস্টেডটাতে না।
Okay, sir.
ওকে। তোমার ফ্রেন্ড কে এখানে? কোন স্কুলের তুমি?
Sir, Farabi. Sir, mastermind.
আচ্ছা, ঠিক আছে। সো এতক্ষণ যেগুলো প্লেসমেন্ট করে লেখাইলাম এগুলো কোনটা কোনখানে গেছে পরে ওর থেকে শুনে আবার লিখে নিবা, বুঝছো? আর
Sir, লিখছি, sir.
আমি তোমার কাছে তো নোট নাই, তুমি তো খাতায় লিখছো।
জি, স্যার।
পরে পরে যখন নোটস পাবা তখন প্রপার প্লেসে লিখে নিবা বা এই ভিডিওটা বের করে ভিডিও থেকে দেখে শুনে শুনে লিখে আবার লিখে নিবা, বুঝছো কি বলছি?
Okay, sir.
এই পেজে যাতে আপডেট করা হয়। আচ্ছা,
Yes, sir, I know that.
আমরা এই জিনিসটা দেখি। আলফা ডিকে তোমরা আগে ও লেভেলসে পড়ছো, এটা হচ্ছে বেসিক আলফা ডিকে ইকুয়েশন। এখানে শেখানোর মতো কিছু নাই, একটা সিম্পল জিনিস এখানে দেখাই, সেটা হচ্ছে যদি সামহাও এখানে একটা নাম্বার থাকে, মনে করো হচ্ছে 2 আলফা পার্টিকেল রিলিজ হয়েছে, তাহলে এটা হয়ে যাবে 8, এটা হয়ে যাবে 4। এই জিনিসটা একটু হিসাব রাখতে হবে। অনেক সময় স্টুডেন্টরা শুধু উপরের রোটা দেখে আর নিচের রোটা দেখে, মাঝখানে এই 2টাকে দেখে না। এই 2টাকে যদি ইফ ইউ ডোন্ট লুক এট দিস 2 then you will be in trouble. If there is a multiply if there is a মানে coefficient in front of the alpha particle number, you have to utilize this for these two changes as well. Similarly, the beta decay, which we have learned earlier in our O levels, this was actually defined as beta decay, or এখানে ব্র্যাকেট একটা জিনিস লিখো, beta minus decay. The beta decay that we have learned in our O levels is actually beta minus decay, because there can be two types of beta decays, beta plus decay and beta minus decay. And we're going to talk about beta plus decay after a while, which you have to write down in this space. So beta minus decay, যেটা হয়, the thing that happens that total nucleon number or mass number of the isotope remains the same. We have one electron shot off from the nucleus. We call this electron the beta particle. We don't call it electron because it was not created from, it is not available from the shell. It is a high energetic electron which is shot away from the nucleus in the process of beta minus decay, and the new product has +1 proton number, and that's why we have the beta particle symbol like this, 0 as mass number and -1 as proton number. -1 in this case doesn't mean this is a hidden or absorbed proton. It simply means that whenever beta minus decay will happen, that produced thing will have one additional proton number compared to the original thing. That's the significance of this -1. এগুলো তোমরা ও লেভেলস অলরেডি শিখছো। এই রিঅ্যাকশনটাকে যদি আমরা এখন ফার্দার ব্রেকডাউন করি তাহলে আমরা কি কি পাবো? হ্যাভ a look at this thing. This reaction is not perfect. This is because in any nuclear reaction, 4 properties must be equal before and after reaction. These properties are baryon number, lepton number, charge, and strangeness. Strangeness is an optional property. Strangeness is only gonna be significant if a strange quark is involved. If a strange quark is not involved, then strangeness doesn't need to be calculated. Strangeness on both sides would be 0 and 0, which is going to be happening for this example. Let's have a look at this example. I'll explain this whole thing, and I need you to see it very carefully. For example, the beta decay of carbon 14 is given by this. Up till your O levels, you have only learned up to this much. Am I correct?
Yes, sir.
Only এই much. এই জিনিসটা অ্যাবসলিউটলি নতুন, সো let me just label this with blue maybe. এই জিনিসটা অ্যাবসলিউটলি নতুন। এই জিনিসটা কোথা থেকে আসছে সেটা আমি একটু পরে বলবো। আপাতত আমরা জাস্ট এই পার্টটুকুর এক্সপ্লেনেশনটা দেখি, so that I can introduce the new information at the proper place. So this is the basic reaction. Carbon 14 decaying into nitrogen and producing one beta particle. So this is the equation that we know. Let's compare the baryon numbers on both things. Baryon number basically means, baryon means in this case the number of proton plus neutron, or we can also say baryon number in this case means the mass number from chemistry. So on the left side we have 14 nucleon number, 14 baryons. On the right side we have 14 plus 0. So the baryon number is equal on both sides. We have this number satisfied. Before and after, that number is remaining same. Let's have a look at the lepton number. Lepton number should also be equal. This is a nucleus. This is not the whole atom. Within this nucleus, we only have protons and neutrons. So practically there is no lepton available. Within this nucleus, we only have protons and neutrons. So there is no free lepton available. So the lepton number before reaction is 0. Within this nucleus, there is no lepton. So lepton number before the reaction is 0, which means after the reaction, it should also be 0. But if you have a look over here, this is also a new nucleus, this nitrogen. So that one has a total lepton number of 0. That's this 0. Whereas this electron is a lepton. That's why it has a lepton number of +1. এখানে এটা প্লাস হবে, এটাকে প্লাস বানাও সবাই। এটা ভুলে মাইনাস দেওয়া হয়েছে। Make this plus. This is the lepton number for this electron. This is the lepton number from this thing. Don't give these arrows. I'm just giving these arrows to make sense with you. Now, disregarding this part, for the time we forget about this part. If we just only look over here, we can see that on the left side we have 0 as lepton number. On the right side we have +1 as lepton number. This is actually not okay. So that's why we gave a crossover here, that this reaction would not make sense. To balance this reaction, either we would require a +1 over here, or we would require a -1 on the right side. Now, essentially, this nucleus doesn't have any lepton, so there is no way we can give this. So this is not acceptable. So the only other logical option is that whenever this reaction will happen, somehow an anti-lepton should also be produced, because we have a detected lepton, and the lepton number must be balanced on both sides before and after the reaction. So somehow this anti-lepton should be released from this reaction as well. That was the scientist's guess for a pretty long time. Then, as the technology of detection got improved and improved and improved further, then the scientists eventually came to find out, yes, there happens to be an anti-lepton which was named as anti-electroneutron. Have a look. This is the symbol for neutrinos. Let me just take you back to the table. The symbol for neutrino is the small mu. This is gamma, and this is small mu. Let me just show you the difference in type. Where is the browser? This is mu. I think that was nu. Where is the new sign? AJ. This is the new sign. Bit of like a V, but not essentially like a V. It's a Gita alphabet, so it's new. And capital nu is basically N, and the small nu looks like this. So all of these neutrinos has a generic symbol of nu. So both electroneutrino has a symbol of nu, but because it is electroneutrino, there is a subscript E. So electroneutrino is written like nu E. Mu neutrino is written like nu mu. So this is mu neutrino. Tau neutrino is written like nu. This is the symbol for basic neutrino symbol, and then at the subscript tau. These three are the symbol for the lepton particles. But if we want to represent their antiparticles, simply we're going to give a bar sign on top of it. This is anti-electron neutrino. This is anti-muon neutrino. This bar sign makes it anti-tau neutrino. These names are pretty long. They are a mouthful, but that's the way scientists have named them. So we have to bear that. We have to get okay with this. Naming এর অ্যাসপেক্টটা বুঝা গেছে?
Yes, sir.
দেখো, কোশ্চেন থাকলে আমাকে বলো। So what the scientists eventually found out, that whenever this nuclear reaction actually happens, one anti-electron neutrino comes out of here, out of this reaction. And you can see over here, like I told you earlier, that typically electron and anti-electron and electron neutrino, they are very closely attached. In this case, you can see that electron and electron neutrino are not closely related. Electron and anti-electron neutrino are closely related, because these two things are going to be emitted out of this carbon-14 atom simultaneously, making the total lepton number 0 on the right side as well. So whenever we attach this -1, only then this whole thing becomes perfectly 0. This cross sign was given before I introduced the anti-electroneutron. That's why the cross sign is still here. The cross sign is over here to give you an idea that from our O-levels understanding, up till only this much, the reaction does not actually fulfill our requirement. Up till this much, adding the new thing that we have just learned, that if the presence of anti-electroneutrino, then the electron number becomes -1. So now the whole thing is becoming 0 and satisfies our requirement. এইটা বুঝা গেছে কিনা এই পর্যন্ত এভরিওয়ান? এই পর্যন্ত বুঝা গেছে কিনা?
Yes, sir.
Charge. The third property that we're going to check for is charge. This is the carbon 14 nucleus. What is the charge of this whole thing? What do we have within this thing? We have 8 neutrons and 6 proton. Neutrons are neutral. There is no charge. Protons, 6 protons have +6 charge. So you can see that we have used the symbol as well, +6. To be honest, in the baryon number, we should also use +14, and also you should also use +14. Somehow the plus was not given. I recommend that you give the plus over here, because all of these numbers have their plus and minus values. Baryon number can be plus or minus for different type of particles. So plus is a part of their identity. If you don't want to give plus sign, it's okay. In many cases, your marks would not be detected, but I highly recommend that you write them as +14. চার্জের জন্য তো অবশ্যই প্লাস মাইনাস দিতে হবে। চার্জ প্লাস মাইনাস দেওয়ার সাথে চার্জ কোনোদিন লেখা যায় না। সো the charge of the initial carbon nucleus was +6. The nitrogen nuclei has a charge of +7, and the electron has a charge of -1. So if you just balance this on both sides, just from our earlier knowledge of O levels, this 6 equals to 6 +6 equals to +6 balances out. And since this entire reaction does not have any strange quark involved, so strangeness is 0 on the before the reaction, also 0 before after the reaction. So this is also this optional condition is also essentially fulfilled, because there is no strange quark involved. So practically these are the 3 core things that we are taking for this one, because for this reaction, because strange quark was not involved within this reaction. But if strange quark was involved, that number has to be equal on both sides. If this was 1, this one has to be 1. If this one was -1, this one had to be -1. If this one was +100, this one had to be +100, like that. So এটা হচ্ছে in gross terms. Now over here we are trying to break down this equation into much smaller portions. Have a look. This reaction can be further written as 8 neutron plus 6 proton converting into 7 neutron plus 7 proton plus the rest of the things. এখানে ডট 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 মানে হচ্ছে এখানে আছে হচ্ছে একটা ইলেকট্রন, মানে ইলেকট্রন না, বেটা পার্টিকেল, আর তার সাথে একটা অ্যান্টি ইলেকট্রন নিউট্রিনো। সো ওই জন্য এখানে ডট 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 দেওয়া আছে। সো উই বেসিক্যালি ব্রোক ডাউন the at the atomic structure, nuclear structure of carbon nucleus and the nitrogen nucleus. So we wrote them as plus signs. If we get rid of the redundant parts or unaffected parts over here, you can see over here, here we have 8 neutrons, here we have 7. So if you subtract 7 neutrons from both sides, you get 1 neutron remaining. And here we have 6 protons and 7 protons. So if you subtract 6 protons from both sides, because they are unaffected, we basically have 1 proton on the right side. So if we get rid of the redundant part, which did not actually take part in the reaction, we actually have this reaction, that 1 neutron converts into 1 proton, emitting out 1 beta particle and 1 anti-electron neutrino. Anti-electron neutrino, এই দুটো নাম্বার হচ্ছে 0, because they don't cause any mass number change, or they don't cause any proton number change. So these two numbers are always 0 for anti-electron neutrino or electron neutrinos, for example. এই রিঅ্যাকশনটা বুঝা গেছে? এটা কিভাবে হলো বলবান? এই রিঅ্যাকশনটা বুঝা গেছে কিনা?
জি স্যার।
এখন
স্যার
আমরা
এখন যে পার্টটা বললাম ওই পার্টটা কি আরেকবার বলবেন?
we broke down the nuclear structure of these two nucleus, carbon 14. So what are the particles do you have within a carbon 14?
7 neutrons and 7 protons.
Bull. Carbon 14 6.
ও আচ্ছা সরি আচ্ছা সরি 6 protons আর 8 neutrons, আমি নাইট্রোজেন শুনেছি।
এখন বাকিটা বুঝে ফেলছো তাই তো?
Yes sir.
বাকিটা বুঝা গেছে, okay. Now if we break down this thing even further, if we break down the neutron into the quark model, neutron was produced by up down down, which you have seen in the earlier page, and proton was created by up up down, which you have seen in the earlier page, and the rest of the part remains same. Now from these two sides, if you get rid of the redundant parts, which actually did not involve in the equation, you can see that we can cross out one up on both sides. We can cross out one down and one down on both sides. So what we are left is one down quark converting into one up quark and emitting one beta particle and one anti-electroneutron. This is the quark level structure for one beta minus decay. এই পর্যন্ত বুঝা গেছে কিনা? This was the nuclear reaction using the nucleons, the entire nuclide notation. So these are we use this was a more macro scale. Then we got rid of the extra proton and neutron, and we could write the equation also in terms of neutron and proton only. And then if we break down the neutron and proton in their quark variation, quark structures, up down down and up down, then we can get to this final stage. So ultimately what it means that whenever the carbon 14 decays into nitrogen 14 and produces one beta particle and one anti-electron neutrino, the actual reaction is that one down quark breaks down into one up quark and also this thing also produces one beta particle and also emits one anti-electron neutrino. So একটা ডাউন কোয়ার্ক ভেঙে এই তিনটা জিনিস ক্রিয়েট হয় এবং ওই তিনটা জিনিসের এই রিঅ্যাকশনের জন্যই কার্বন চেঞ্জ হয়ে নাইট্রোজেন হয়ে যায়। Is it clear so far?
Yes, sir.
Any question? পোলাপান? আচ্ছা এখানে একটা সেন্টেন্স লেখা আছে দেখো, antiparticles are represented by a bar sign on top except anti-electron which is called a positron. The reason আচ্ছা এখানে একটা জিনিস বলি সেটা হচ্ছে electron sign for the longest period the scientists decided was given by E minus because electron was a negatively charged particle. Scientists actually came across this whole antiparticle concept and found out the existence of these antiparticles far later, and they decided that, well, if we have up quark, then we're going to have anti-up quark and we're going to represent them as a bar. They adopted this sign notation, which worked out. Then they come to the problem that, well, how do we represent the antiparticle of electron? Are we going to write it as E minus bar? This is just not okay because apparently there are two horizontal lines on top. So, and also positron was pretty much one of the very earliest antiparticle scientists found out. So they thought that there can be a lot of different type of particles like these. So they decided that the antiparticle of the electron would have an individual name. They decided to call it positron, and the sign of positron was designated to be E plus. So electron is E minus, antiparticle of electron is E plus. So this is the only notation that is slightly different from the other ones. For all the other antiparticles, you just have replace a bar. So up quark is U, anti-up quark is U, electron neutrino is like this, anti-electron neutrino is like this, and so on and so forth. Exclusively for the electrons antiparticle, we call it positron, and its symbol is given by E plus. এটা একটা ইনফরমেশন, এটা এমসিকিউ এর জন্য অনেক ইম্পর্টেন্ট, পেপারটাতে খুব মাঝে মাঝে আসে, বাট পেপারটার জন্য খুব একটা ইম্পর্টেন্ট না, এমসিকিউ এর জন্য অনেক বেশি ইম্পর্টেন্ট। The last thing that we have to learn for the AS level, new thing for our AS level atomic physics is beta plus decay. Beta plus decay happens to be just the opposite reaction of this one. So to make sense what this is, you're going to eventually write this stuff over here, but let me just explain first, and then I'm going to ask you to copy this part. I'm going to take out this equation over here and show you what is happening. So have a look. In this equation, we're having down quark converting into up quark, producing one beta particle and producing one anti-electron neutrino. ঠিক আছে? The beta plus decay would be exactly opposite, which means if I simply take a look at this conversion, I'm going to edit this formula. So if you simply give an opposite sign, this is actually the beta plus decay. This is actually beta plus decay, which means one up quark would be converted into one down quark. So all of these three things will merge together to produce a down quark. Now this might actually look weird that I'm saying weird because we always define the nuclear breakdown process that there is a initially existing single entity that produces a lot of fractions. We don't usually work by that there are multiple different entities which merge together to produce a new thing. This is exclusively applicable for fusion, but not for beta, not for natural decay. Natural decay process is defined with the basic concept that initially you have a whole thing that breaks down into other things. That's the idea. So what the scientists decided, okay, fine, we're going to first rewrite this equation. So let me just rewrite this equation. Up quark plus one electron plus one anti-electron neutrino produces a down quark. I just changed sides and change the direction of the arrow. And then they decided that we're not going to write these things over here. We are here, or we're going to place them over here. So if we do the side change, all of these particles should be converted to reverse version. Reverse version is basically means that all of these particles have to be written as antiparticles. So have a look what I'm doing. Let me just erase this part. No. So have a look over here. If I am going to change their sides, up quark should be converted into a down quark. Here we had an electron or a beta particle. So whenever this would be reversed on the side, this would become an anti-electron or a positron. Here we had an anti-electron neutrino. So this is going to become an electron neutrino. This is the total reaction that happens for a beta plus decay, which means one up quark converts into a down quark. Additionally, it produces one positron and one electron neutrino. This reaction is what we call the beta plus decay. Beta plus decay is actually quite interesting. We cannot recreate beta plus decay in our earthly environment. because this is an extremely energy demanding process, like superbly energy demanding process. Let me tell you why this happened. What I need you to understand, just have a look. What I need to understand, just have a look. Whenever down quark was converting into up quark, let me use a different color. Whenever down quark was converting into up quark, be a bit thickness, we had one neutron converting into proton, right? এই জিনিসটা খেয়াল আছে? নিউট্রন থেকে প্রোটন হচ্ছিল, তাহলে আমাদের কি হচ্ছিল? প্রোটন নাম্বার বাড়তেছিল, ঠিক না? এই যে প্রোটন নাম্বার এখানে বাড়তেছিল, নাইট্রোজেন প্রোটন নাম্বার ছিল কার্বনের থেকে এক বেশি, ঠিক আছে?
জি স্যার।
6 থেকে কি হয়েছে? 7 হয়েছে। So if we have the reverse thing, essentially I can write that this up and down can be, this up could be written as up down, and this down could be written as no, sorry, yeah, this up could be written as up down. I'm adding one UD, and if I add another UD over here, this could be written as up down down. So adding UD on both sides, the same thing. So this essentially means that this would actually become a proton, which would be converting into one neutron and emitting one positron and actually producing one electron neutrino. This is a process in which a proton would convert into a neutron. A proton converting a neutron essentially means that the total mass number would remain the same, but the atomic number will decrease. This essentially happens for a dead star which has emitted out a lot of its energy in the process of fusion and everything. It does not have any much hydrogen remaining at its core. So, and it has also undergone the process of supernova. So it has puffed up its outer layer. But still, that core of the whole dead star has so much mass. Try to understand this idea. That core, that remaining core of that dead star has so much mass that the gravitational force is really strong. How strong? The gravitational force is so strong that the structure of atom is dissolved. Because of gravitational force, the orbital electrons are pulled towards the nucleus and they get absorbed within the nucleus. So if you wonder how does the electrons get absorbed in the nucleus, where do they go? That's basically what is shown over here. Have a look. One up quark absorbing one electron and absorbing one anti-electron neutrino produces what? Down quark. Or in other words, you can say one up quark converts into a down quark, producing one positron and one electron neutrino. Now have a look. If within this process, one up quark is fed with an electron, this electron will merge with this positron. Together they will merge, and what will happen? Whenever a particle, they will annihilate each other. Exactly, they'll annihilate each other and they'll convert into pure energy, which basically means this electron is basically gone, and this proton converted into neutron, which means within this, because of the gravitational force, the structure of atom is gonna get dissolved, and as a result, the electrons are gonna get the orbital electrons are gonna start falling into the nucleus, and the nucleus is gonna absorb them all together. They're not gonna let them go, and all the protons are going to slowly start converting into neutrons. The reason they have to convert into neutrons, hear me out. You do understand that protons are all positively charged, so protons do repel, right?
Yes sir.
Protons have a tendency
Yes, sir.
to split out from within the nucleus. They have a tendency because all the protons are positively charged and they are packed within a very small containment within the diameter of the nucleus. So protons, because all protons are positively charged, they have a tendency to repel each other and break free. They have a tendency. They don't do that, but they have a tendency. The reason they cannot do that is because of the effect of the nuclear force. A strong nuclear force and weak nuclear force, they do some different kind of interactions, which I'm not getting into in detail. But because of the strong and nuclear force, those two forces together actually overpower the repulsive force between the protons and actually keep the whole nucleus stable. So that nuclear force is basically responsible to keep all of those highly charged protons within that small distance. So now try to think about this process for the dead star's corpse, which is the entire core, where the gravitational force is causing the entire atom structure, the orbital electrons, to fall onto the nucleus, and all the protons are slowly converting into neutrons. You might wonder, what's the benefit? Well, here's the deal. Neutrons are neutral. They don't repel, which means you can actually pack a huge number of neutrons side by side without any inherent force within themselves, is it not?
Yes, sir.
You cannot pack a lot of protons within a very close encampment because they are going to naturally repel each other, but you can actually pack a lot of neutrons within a small space, and that is going to be that is going to work pretty well. So that's essentially what happens over the time. Because of the gravitational force in that dead star's corpse, I mean the remnant of that dead star, the orbital electrons slowly starts to get absorbed within the nucleus, and the protons slowly start to convert into neutron. And as the process slowly goes on, because of these annihilation processes, you have a look at this annihilation that we just talked about, that star emits out energy. Every once in a while it emits out some energy, and slowly but surely it continuously loses its proton number and it increases neutron number. Over the time it happens that it converts all of its proton into neutrons, and in that stage we call it a neutron star. Or also, as the decay goes on, as this beta plus decay happens within that star, for that duration also we call it a neutron star. A neutron star is basically continuously converting its protons into neutrons so that it can keep all of those particles within very close to each other, because of the strong gravitational force is actually squashing them into the whole object. The density of a neutron star is extremely high, like super high, because you need to understand this thing. Atom is mostly what?
Space.
An empty space?
Atom is mostly
Empty
empty space.
space.
Atom is mostly empty space. So practically speaking, all the density of a physical object that we experience, metal bolo, plastic bolo, light object bolo, whatever, all the density that we see is basically affected by the whole empty space. The mass of the nucleus is the actual mass, because electrons have very negligible mass compared to the mass of the nucleus. So the nucleus pretty much provide all the mass for an atom, whereas the orbits pretty much provide all the volume of the atom. So whenever that orbit actually gets destroyed, which means all of that mass is practically now within that confinement of that nucleus, which means the volume has become super shrinked. So the density goes super high, right? One of the
Yes, sir.
one of the comparison that one of the scientists actually gave at a time I came to read across it is that if we take 1 teaspoon of material out of a neutron star, that would be as heavy as the entire Earth, or was it the entire solar system? I actually forgot. Let me just Google that. It's that heavy. I mean, heavy in this case, I'm trying to mean in alternative to that the neutron star is extremely dense. This one neutron star material would weigh 4 billion tons. Until now, white dwarfs are seen to 4 billion tons. 4 billion tons. Let's try to find out mass of solar system. In ton. যাই হোক, আমি মানে এই কম্পারিজনটা ভুলে গেছি এক্স্যাক্টলি, বাট দ্য পয়েন্ট আই এম ট্রাইং টু মেক দ্যাট নিউট্রন স্টারস আর এক্সট্রিমলি ডেন্স। এইটুকু পর্যন্ত বুঝা গেছে কিনা?
Yes, sir.
And because and to achieve this
Sir.
beta plus decay, we need so heavy strong attractive force that it is impossible to recreate within an earthly environment. We don't have that kind of capabilities to produce that kind of strong force. So it is only seen in the nature and exclusively for a neutron star. Scientists saw this thing and they couldn't figure out that how this happened, and then eventually over the years of research and hypothesis and observation and research, they actually came to understand that this whole star is practically undergoing beta plus decay, where protons are continuously converting into neutrons. Ultimately the whole thing is slowly getting converted into neutrons. So that's the whole idea of beta plus decay. এই পর্যন্ত বুঝা গেছে কিনা? কথাবার্তাগুলো বুঝা গেছে কিনা? আচ্ছা,
জি স্যার।
এখন যে কাজটা করবা, তোমরা এই যে বেটা প্লাস ডিকে ইন কপি লেখা আছে না, এটা কেটে দাও। কেটে দিয়ে এখানে এই তিনটা ইকুয়েশন লিখবা। আমি মার্ক করে দিচ্ছি কোন তিনটা ইকুয়েশন। আগে লিখবা হচ্ছে এইটা, তারপর লিখবা এইটা, তারপর লিখবা এটা। সো রাইট দিস ওয়ান এন্ড দিস ওয়ান, এই তিনটে ইকুয়েশন দেখে দেখে লেখো, লেকচার থেকে দেখে দেখে লেখো। এবং তারপরে লিখবা হচ্ছে এইটুক। বাবা কোন করে কেন বাবা, কোন করে না। ইকুয়েশন একটা লিখে নাও, তারপর আমি অল্প একটু ডেসক্রিপশন লিখাবো এন্ড দেন উইল কল ইট এ ডে। Give a long horizontal line over here and write the heading beta plus decay discussion. লিখো beta plus decay is the opposite of beta minus decay. Uzma, okay. Beta plus decay is the opposite of beta minus decay.
Assalamu alaikum, sir.
Walaikum salam. Beta plus decay is the opposite of beta minus decay. Full stop. As the equations represent, by this reaction, as the equation represent, comma, by this reaction, one proton converts into one neutron. One proton converts into one neutron. Full stop. This happens naturally in the remaining core of dead stars. This happens naturally in the remaining core of dead stars where the gravitation force is so strong that orbital electrons collapse into the nucleus. collapse into the nucleus. Protons absorb these electron and converts into neutron.
Sir, protons কি?
Absorb this electron. One proton absorb one electron, that's obvious. Protons absorb these electrons plural লেখো, দুইটা plural লেখো. Protons absorb these electrons and convert into neutrons. Full stop. In other words, proton converts into a neutron and emit in other words proton absorb these proton converts into a neutron, sorry protons না singular plural মানে ম্যাচ করো, এই লাইনটা সিঙ্গুলারে লিখবো. In other words, one proton converts into one neutron. In other words, one proton converts into one neutron and releases one positron and one electron neutrino. Full stop. The absorbed orbital electron and created positron, the absorbed orbital electron and created positron annihilates each other and creates pure energy. Which is emitted from the thing.
From the
Thing. THING. আমি এখানে লিখতে পারতাম which is emitted from the কি বলো dead stars remaining corpse, এই পুরো কথা লিখতে পারতাম, but don't do that. Which is emanated from the thing, full stop. This remnant core is called a neutron star. This remnant core is called a neutron star. Full stop. Last sentence likho. It is impossible to recreate this reaction on Earth. It is impossible to recreate this reaction on Earth because of such high requirement of gravitational force. Because of such high requirement of gravitational force. Because of such high requirement of gravitational force. And পুরোটা একবার পড়ে দেখো এই প্যারাগ্রাফটা, কোনো কোশ্চেন থাকলে জিজ্ঞেস করো, কোশ্চেন না থাকলে ক্লাস শেষ। পুরোটা একবার পড়ো সবাই।
এনার্জিটা হিট এনার্জি না?
It is usually emitted as radio frequency pulses. I mean, why is it a radio frequency pulse? That's a totally different story. But you can look up the observed behavior for neutron stars in Google and or Wikipedia and read it through. It's usually radio frequency pulse. মানে জিনিসটা হচ্ছে এরকম, জারিফ তোমাকে বোঝানোর জন্য বলতেছি, সেটা হচ্ছে যে মনে করো নিউটন স্টারটা একটা স্টেজে আছে গ্র্যাভিটেশনের জন্য, তো পার্টিকেলগুলো কাছে আসতেছে আসতে আসতেছে কাছে আসতেছে। There would come such a point when one orbital electron from a lot of the nucleus are gonna drop almost simultaneously to the nucleus, and that will produce a surge of energy within the neutron star, which will be emitted at that instant. And once that compression happens, the gravitational force lets go a little bit because you just absorb the whole thing. Then the gravitational force builds up once again, and then after a while it does that whole thing one more time, and then there is another surge of energy. So it usually doesn't happen continuously. It happens like compression, that kind of thing. Does it make sense?
Yes, sir.
Now, why does it behave like this? I honestly don't know. I didn't study about this, but if you're interested, Google that. এই প্যারাগ্রাফটা সবাই বুঝে গেছে? কার কোনো কোশ্চেন?
প্রোটন আর অরবিটাল ইলেকট্রন গুলো কি মার্জ করে একসাথে?
Yes. That's why I wrote both of these equation, that up quark absorbing the electron and also the anti-electron neutrino converting to a down quark. ওটাও একটা logical version. Or if I want to place everything on the other side, I can say up quark produces a down quark, releasing a positron and an electron neutrino, and that absorbed electron and the positron annihilates. So জিনিসটাকে দুইভাবেই জাজ করা যায়। মনে রাখার জন্য দুটো এক্সপ্লেনেশনই ইউজফুল। Depending upon the question variation, you can actually use either of these expressions. বুঝতে পারছি?
জি স্যার।
সো কার কোনো কোশ্চেন নাই? সো আজকে ক্লাসে এইটুকু পর্যন্ত থাক। ইনশাআল্লাহ কালকে আমরা এই টপিকের উপর বেস করে কিছু ইয়ার কোশ্চেন সলভ করব। আমার যে ওয়ার্কশিট অ্যাকচুয়ালি কোয়ার্ক স্ট্রাকচারের কোনো প্রবলেমই দেওয়া নাই, কারণ কোয়ার্ক স্ট্রাকচার প্রবলেমগুলো সিলেবাসে ইনক্লুড করছে হচ্ছে 2015 থেকে, whereas my worksheets are compiled up to 2013. সো এই টপিক বেস প্রবলেম পাইতে হইলে আমাদেরকে ইয়ার কোশ্চেনগুলো রিসেন্ট ইয়ার থেকে ব্যাকওয়ার্ড সলভ করতে হবে। সো আমি নেক্সট ক্লাসে এই ধরনের কিছু কোশ্চেন জড়ো করে রাখবো যাতে করে আমরা ইমিডিয়েটলি কোশ্চেনগুলোতে জাম্প করতে পারি। I'll discuss some interesting problems hopefully in the next class, that is tomorrow.
স্যার,
Yes.
লিখেছেন মানে লিখতে বলেছেন যে অরবিটাল ইলেকট্রন আর পজিট্রন হচ্ছে দুইটা অ্যানাইলেট করে মানে
Yes.
একজন আরেকজনকে, তাহলে ইকুয়েশনে হচ্ছে পজিট্রন কেন লিখবো?
Well, equation of positron আমরা লিখলাম তার কারণ হচ্ছে this proton is creating a positron which gets added to the external electron that came into the nucleus. External electronটা তাই প্রোটন থেকে ক্রিয়েট হয় নাই। মানে ঘটনাটা হচ্ছে এরকম, আমি যদি
বুঝতে পেরেছি।
হ্যাঁ, ঘটনা হচ্ছে এরকম, মনে করো আমি ঘরের ভিতরে একটা পজিট্রন নিয়ে বসে আছি, এখন দরজায় একটা ইলেকট্রন এসে নক করলো, আমি সাথে সাথে পজিট্রনটা দিয়ে দিলাম। সো তারা দুজন মিলে এনার্জি হয়ে গেল, আর আমি আগে ছিলাম প্রোটন, আমি কনভার্ট হয়ে গেলাম নিউট্রনে, এরকম। বাট ওই ইলেকট্রনটা আসার আগ পর্যন্ত পজিট্রনটা ক্রিয়েট হবে না বা রিলিজ হবে না। বুঝে গেছে?
জি স্যার।
বিউটিফুল।
স্যার,
হ্যাঁ বলো।
স্যার এই যে কালকের ভিডিওটা আর আজকের ভিডিওটা একটু আপলোড করে দিন।
আচ্ছা ঠিক আছে, আপলোড করে দিচ্ছি বাবা। থ্যাংক ইউ
Thank you,
ফর
sir.
রিমাইন্ডিং মি। গুড নাইট।
আসসালামু আলাইকুম স্যার।
ওয়ালাইকুম
গুড
আসসালাম।
নাইট স্যার।